Hi, everybody. It's Keith. It is Thanksgiving 2010, and I just want to say thank you to everybody for all your really kind words and support. It's been fantastic. I made this little presentation on base 2 operating systems for binary. IP addresses are basically representations with IPv4 of binary numbers. And so I did a little presentation. It's about 8 to 10 minutes long. I think you'll enjoy it. Taking a look at the differences between base 10 and base 2. If you're just getting into IP addressing, I think you'll find it valuable. And again, happy Thanksgiving, and thanks for all the kind words. Let's do a little reminder of the numbering system that we work with. If somebody came up to you and said that something costs $832,807 written out like this, we would know exactly what that means. Okay, great. $832,807. Got it. Well, our brains, because we're wired that way, we understand exactly what that means because it's base 10. Here's what's happening behind the scenes. In this position right here where we have the 8, that's the 100,000 position. And we have the 3 in the 10,000 position. Or we can start down here. The first digit is the ones position. And because it's base 10, the next place over is the 10 position. And you keep multiplying by 10, by 10, by 10. And that's why 832,807 is 832,807, because we have 8 100,000s plus 3 10,000s plus 2 1,000s plus 8 100s plus 0 tens plus 7 ones. So if we add those up, 800,000 plus 30,000 plus 2,000 plus 800 plus 0 plus 7, it's 832,807. Now you might say, Keith, why did we even do that exercise? That's kind of lame. We already knew just looking at the number what it meant. Well, I want to be friendly in the event that we get invaded by aliens. And maybe these aliens only have 6 digits at the end of their arms. And maybe they have a base 6 operating system or a base 6 numbering system. If we wanted to do business with them and they're using base 6, we'd want to make sure we can calculate and understand what their values mean and convert it. So, for example, if these aliens were using base 6, here's what would happen in their world. They would be using digits of 0 through 5, and every time they got higher than 5, they would carry the 1 and it would continue. But their values in each of the positions would be different. In the least significant position, it would still be a value of 1, but because they're using base 6, the next position over would be times 6. So where we had 10 in our tens position, they would have a 6th position. And the next value over would be times 6 and times 6 and times 6 and times 6. It goes the other direction too. We could say that this value divided by 6 would be this position, and divided by 6 and divided by 6 and divided by 6. Same as ours, except they're using base 6 and we're using base 10. See how simple that is? Well, let's say that they wanted to sell us something, these aliens, and they wanted to sell us something that was 250342. That's the number they gave us. Well, how much is that in decimal? Well, we could break it down. We could say, well, we know what the values are of these positions. Let's just line them up. We've got 2 of the 7,776 for a total of 15,552. We have 5 of the 1296s, which equals this. We don't have any of the 216s, so that'd be a 0. We have 3 of the 36, which is 108. We have 4 6s and 2 1s. And we'd add them all up. And that would tell us, oh, wow, check it out. The number 250342 in base 6 has a decimal equivalent of 22,166. So we would know now what that actual value is or what the cost is. Is that weird? It's absolutely weird. But what I'm trying to do, what I am doing, is I'm encouraging you to stretch a little bit, to expand your horizon in case we get met by aliens so we can do conversions with them. All right, so let's just do one more. Let's say, hypothetically, we were invaded by an alien race, and this alien race only had 1 finger on each arm, and they had 2 arms. I should also clarify that. What would they use for a base numbering system? Probably they would use base 2 because they have 2 digits. So with base 2, let's just keep thinking here. With base 2, they would use digits 0 and 1, and anytime they went higher than 1, they would carry it over to the next placeholder. And their values would be, the least position right here would be 1, just like decimal and just like base 6. Their least significant position would be a value of 1. And then because it's base 2, you just multiply it to identify what the next values are. So base 2, the next position would be a value of 2, and then times 2 more, 4, and then times 2 more, 8, 16, 32, 64, and 128. Now these folks from the alien culture where they only have 2 digits to play with, they're not going to have a whole bunch of variety here because they can only use digits 0 and 1. That's it. So if they gave us a number like this one, 10101100, we could say, holy cow, is that the price? They say, yes, that's the price. Well, how do we calculate in decimal what that value is? I mean, that's really weird. Well, we'd break it down. We would say, well, let's line up their value system, and the decimal values of each of the bit positions are the positions they're using, and we can say, okay, great. This is the 128 position. They've got 1 of those, so we'll take 128. They've got 0 in the 64 position, so none of those. They've got 1 in the 32 position, so 32. 0 in the 16 position, so none of those. And then we have 18, 14, no 2s, and no 1s. And if we add those up, 128 plus 32 plus 8 plus 4 plus 0 equals 172. So it's a little bit challenging to deal with these aliens with 2 digits, using 0 and 1s. So why do we actually tell this story? What I'd like you to do is to make sure that you're comfortable in understanding how to convert the base 2, which is called binary, into decimal. And the reason for this is because we happen to be developing and doing IT support for an alien culture called computers. They have 1s and 0s that they deal with. And the reality is that when we have things like IP addresses, although they are represented to us in decimal, like we might have one part of our IP address that says 172 dot something, that 172 to us is actually this string of 1s and 0s to the computer. This is the alien race that we're dealing with, is our computers and the networks that we deal with. So here's an example of an IP address that we might typically see on one of our computers. It's 172.16.1.40. Now we call it dotted decimal. And what that really means is, see this comma up here, how we use this comma? This value up here with the comma is just to help us visually see the separation point. It doesn't really change the value of it. It's just representing the fact that that's the thousands position. And it's just a convenience that we use. Down in dotted decimal, each of these numbers is representing 8 bits. In fact, the 172 is being represented by this string of 8 bits right here, 10101100. I also repeated it here as well, and I color-coded it. So that's like a purple or a cyan color, and here's the bits representing it. Then the period basically says that part is over. So my 172 is these 8 bits. Then I have a period, and then I have a 16, which is another 8 bits. So if we took 16 and figured out the 1s and 0s for it, it would equal this. That 16 is pretty easy, actually. We just have a 1 on in that position right there, and everything else is a 0. So that's a 16 in binary. And then we have the next octet. They call each section of the IP address an octet because it has 8 bits. So instead of saying, hey, this section of the IP address, we might call that this octet, the third octet. So 1 is also pretty darn easy. It's all 0s here and a 1 on in the 1's position. So that's this octet of 1 in binary. And then the last piece is the .40, the last octet. So we have no 128s, no 64s. There's 132 in that, plus 8 more in the 8th position, and that equals our wonderful whopping 40. So that's it. Mystery solved. No problem. Life is good. That's how we make sense of the actual IP addresses. They're in binary. We use decimal. We write them in decimal, but they're actually representing an IP address in binary. Now, the other part of this story that we absolutely want to chat about is part of this IP address is the actual network or street that a host lives on. And that would be on the left side. So something on the left, some of these digits on the left are the network, and some of these digits on the right represent the actual host, like a house number on that street. Now the question is, where's the line? Is it 172 is the network and 16.140 is the host address? Or is 172.16 the network and 1.40 is the host? Or is 172.16.1 the network and 40 is the host? Where's the dividing line? Where's the line in the sand? The line in the sand is drawn by something called the mask. And you can call it whatever you like. You can call it the subnet mask. You can call it the mask. The mask does one thing for a living. It identifies where the actual network portion of an IP address starts and stops. That's what it does. And here's how it works. The mask is also represented here in decimal, dotted decimal. So if we break it out, we take 255, that's going to equal 8 ones. And everywhere where there's a 1 in the mask, it basically is claiming the corresponding bit and saying that bit of the corresponding IP address is part of the network address. So that means first 8 bits are all the network address. The second 8 bits, the second octet, are all network address. The third octet, because the third octet is also 255 in decimal, all ones in binary, mean the third octet is all network bits. So here's what's left over. The line in the sand is right there. When the mask bits end, it's basically saying everything after is available for host addressing. So in this case, we could say that this computer that has this IP address and this mask is on network 172.16.1. And usually we're going to write out the full octet, the full IP address. So we could say it's on 172.16.1.0 and the host address is 40. There's a logical AND process that goes on with these bits if that's important to you. But the dividing line is identified by the mask. When the bits of the mask stop, that's where the actual drawing line is between the network IP address portion and the host address portion. Another thing that we might see is we might see an IP address represented in the CIDR notation with a /24 like right here. That /24 simply says the first 24 bits of the IP address are being used as the network address, which leaves the last 8 bits. So whether we see a mask like this or a mask like /24, these two mean the same exact thing. They also, down below, we could say that the computer is on the 172.16.1 network by simply ignoring these bits for a moment while we describe the actual network address that they're on. And then the computer we could say is on .40. But normally we would actually say the computer is 172.16.1.40 /24 because that gives a full picture of the network that PC is on and also a representation of what the host bits left over are. And that's a quick primer on the world of IP addressing and some of the binary to decimal conversion behind it. Good news, though, we don't ever have to deal with base 6. That was just an example to get your mind expanded a little bit towards the concept of using a different base numbering system. Thanks, everybody.